So the link is working, and the keyword that is here is transfer function of a forced pendulum. That's it. I've inserted in this lecture some slides about general linear theory, linear system theory. Let's go through them now so that we can understand in my logic they were coming after, but maybe we can explore them now. Very basic idea, and this is valid for every linear system. Now, is the pendulum a linear system?
Yes.
Is it? Can we measure time with pendulum?
Yeah.
Are we sure? If I start from here, we cannot at the beginning because it's not linear. But when the sine of the angle is
It's very small.
very small, so okay, we can linearize the differential equation of the pendulum, and we can build. You do remember?
Yeah.
Yeah. Okay. So when the sine of the angle is okay for lazy people, then the equation of the pendulum and the forced pendulum is becoming linear. So it's a linear system. And for a linear system, these are the properties that are valid. We have used this concept here in time domain. If you insert a delta inside the linear system, we get a response. We call it impulse response, and we can build any response by convolution. Okay? We called it the Green's function. Actually, we developed this idea for more complicated linear systems like a solid. And we studied the elastodynamic Green's function. And it was a function of space, time, and direction. Is it okay? Good. So, impulse response, arbitrary response convolution by the Green's function. What is funny is that the convolution, and this is called the convolution theorem, if you look at convolution operator and algebraic product operator, they can be exchanged between time and frequency domain and vice versa. Okay, so what is a convolution in one domain becomes a product in the other. You can do it by hand. I forgot to add a link to this. On the website, I think there is some material, additional material. As far as I remember. Yes. So, for example, you have something here. No, these are the links that I was adding. Okay. And oh gosh. Okay. All the necessary steps are here, and there should be also the convolution theorem. Everything. Okay, I leave it to your, how to say, knowledge, building of knowledge. Okay. Now what is important here? That, by definition, the Fourier transform of the impulse response is called transfer function. So it's, if you want, this. Okay? Yeah. So when I speak about the transfer function of a forced pendulum, I'm just speaking about an equation that now we are going to explore and that we know. And we already solved it. And if you want, the transfer function is something that is telling to you the response of the system, not to a delta in time, but to a delta in frequency. Now, what is a delta in frequency? It's a pure harmonic motion. Okay? Everything is reciprocal between time and frequency. Thanks to Jean-Baptiste Joseph Fourier. Now, do you remember, speaking to you, if we have been had we been solving a linear system with an harmonic series, with an harmonic function forcing?
Yeah.
You should say yes.
Yeah,
Yes.
of course.
Okay, when?
The
No, that's a video question.
damped
Damped harmonic force.
Damped, forced,
was
harmonic oscillator. You remember something about the solution?
Yeah, e to power minus gamma t and multiply with the series video.
The end of the story was the
X equals something.
resonance curve. You don't trust me. Maybe you're right.
Yeah, it should,
It was in the
it oscillates
wave physics.
sinusoidally and then decays exponentially.
Okay, there was one plot that is the key plot for the beautiful. That was the damped. Weak damping, strong damping, energy. Q, definition of Q. I hope you do remember. Forced. And I was shaking in my lap there, okay? The end of the story was this.
Where's the color? Oh, this one.
Good old times. That was the plot of the power absorbed by the system. Power is energy per unit of time. Energy is related to the square of the amplitude of the oscillation. And if you do remember, the resonance curve that is essential also for a building, for every system, is telling to you how much energy can be absorbed by a system when you force it. And I'm sure that you do remember, I think I practiced also this course here, but I can take this one. The length is deciding its omega. How? I'm looking at you because you attended the course.
Equation tells us mass times acceleration is equals to
Do you remember the spring and the mass?
square root k by m.
Over, yeah. Okay, now what about the pendulum? Let's remember, this is Hooke's law. This is inertia.
Yeah.
But the pendulum was a little bit more tricky.
Gravity.
What is the restoring force for this? Is it elastic force? No, it's gravity.
mgls.
So actually, that has to be replaced by G,
by m.
Over L.
but not M. That's Galileo that was telling us, oh look, you can change the mass here, but the period will not change except its
Length.
length. Okay? That's strange. By the way, so once you define the length, you decide the gravity force. If you stay on the Himalaya mountains or in abyss, it will change G, but that's given. Okay, then you can decide to force it. Omega 0 now is given. I can force it very fast, but amplitude is not that much there, and it is out of phase. I can force it at very long periods, it's following me, but no relative motion between the frame and the mass. Or I can force it at this period. Wow, almost no motion here, but a large amplitude there. That's a resonance, okay? It has a peak. According to the damping, that peak can be moved a little bit, but actually it's very near to omega 0. Okay, you can call that the transfer function, because we obtained this inserting an harmonic frequency there, an harmonic forcing. Okay. That was the summary of the past lectures. By the way, linear system, okay, if you have two boxes and everything is linear, you have a double convolution or a double product. And that's the base of filtering, for example, okay, that's easy. What's next? Now it's time for us to understand this set of boxes for seismology. Actually, we spent the part of the wave physics course about the structure of the Earth, if you do remember.
Yes.
Ray theory, surface waves, and stuff like that. And we discovered, for example, some Earth model at different scales, global, regional, not local, but you will do it with Stefano in his course. You can call it the Green's function, maybe. It's a property of a medium. What about this? Okay, that's the source. Can I not? Maybe it's a single force, maybe it's a double couple, maybe it's a fault. Is it linear? Yes, we adopted that case and we developed the representation theorem. What about the last one? Okay, we are going to build that, so maybe we know that. It's the last step of the convolution. So the response that you are getting from the Earth after that source is exciting some waves that are traveling inside the medium. Okay, that's the final filter. And since we are going to build it, we know how to deconvolve it. And it's easier to perform that deconvolution in the frequency domain because convolution becomes a product. So we have, in principle, we have just to divide by the response function of a seismometer. All of these steps here are based on linear system theory. Let me remember you what is a linear system. It's something that by itself is time invariant. What does it mean? That for example, that the impulse response is constant in time. So I knock on the box, I get an answer, and the day after I get the same answer. So it's time invariant, and these two properties are valid. Multiplication by scalars and addition. That's the definition of a linear system. In our case, we can translate this definition for linear differential operators. Like, a long time ago, we defined the differential equation for the harmonic damped oscillator. That's linear. Or the equations of elastic motion. It's linear. Why? Because we cut all the nonlinear terms, but it's linear. Okay, the key point is this that is called convolution theorem. You can prove it just writing the convolution property by definition. You take the Fourier transform, you change once the variables, and you will see that the result is that the Fourier transform of y of t is the product of the Fourier transforms of a two factors that are in the time domain. That's the base of every filtering operation. Okay? So that's why when you hear about high-pass filter, it means that you're letting the high frequencies in the signal. Low pass, vice versa, band pass. Okay? Let's go back to the real starting point. I know that you love algebra and basic physics, that's it. That's a good old friend because we studied it. What do we have here? For example, a mass and a spring, or a pendulum, with some damping coefficient so that we can build this equation with just one difference, well, two differences. The first, now the frame is moving with the Earth, and the Earth sometimes is going to shake, okay? That's the forcing. That means acceleration, because force is mass times acceleration. So the forcing is the acceleration of the ground. So that's the new part. And now we have a frame. So that's me keeping the pendulum there. I'm moving with the Earth, and the mass of the pendulum, or connected to the spring, is trying to stay in equilibrium for inertia. That's it. So the frame is going to move, and the mass will try to stay. So what we are really interested to, actually, is the acceleration of the ground. But we get the acceleration of a mass. That's what we record. And that's why here u is the forcing, y is the coordinate of the mass, and we want to extract u in some way. That's the damping part. It's, as we assume, but the damping is connected to a Newtonian behavior, Newtonian fluid behavior, so friction is proportional to velocity. That's the forcing, and that's the stiffness of a spring or the length of a pendulum. If you rearrange it, we got the classical equation that we studied in wave physics course, or in any basic physics course, with just two small conventions that are changed. In seismometry, don't ask me why, but they use here two. Okay, just a convention. And, well, the other factors are the same. You can compare this with what we studied classically. And a long time ago, we studied this. Acceleration, damping related to velocity. But gamma was nothing else than viscosity over mass. Okay, the spring and then the force. You see, that was an harmonic. So actually in some way, in some fashion, we studied the Fourier transform, so the transfer function. If you do remember, I told you this is the first example of a non-homogeneous differential equation, because it's not equal to zero. It's something, it's equal to something. It was not a delta, so we have not been studying the Green's function, but actually we studied the Fourier transform of an impulse response, and so we can call it the transfer function. So the physics beyond this expression here is exactly the same. What is convenient is to study the solutions, and we know how to do them, because you, for example, you can knock at a mathematician's door and ask, okay, we have a non-homogeneous differential equation, what should we do? Okay, take the general solution of the homogeneous one plus a specific solution of a non-homogeneous one. It's like the Green's function. In the wave physics course, we studied the transient, and then since we were applying an harmonic force, then we considered a stationary regime. You remember? From your thesis, I guess not. But we can go to the Russell, or is Russell? To the website that I used. Oh, no connection again? Yes. Okay. Damped force, you see force here. Okay. Look, that's very nice. So we have three oscillators here, maybe with the same mass, with the same spring, but they are forced in three different regimes. Here the force has a very low frequency. Okay? So the inertia of the mass can follow. They are going together, like myself trying to move the pendulum at very low frequencies. Here it's fast compared to what? To omega 0. So the inertia is putting out of phase the mass at every time. Here it's forced very near to the frequency, and you see the amplitude. In time domain, that was the situation. The transient, the stationary. The transient, the stationary. But look at the amplitudes. That's resonance. Here, okay, transient, stationary. Another applet, but we've been looking, what is it? Here. And we had been smiling, if you remember, using this applet. Okay. Now you have to imagine that the forcing is the ground. Okay? Let's imagine to build a frame around that spring and the mass, and the forcing is the ground. The ground is, that's not rocket science, come on guys. You seem very fascinated by this applet. Okay. You two should remember that we tried to play a game here For example, I was putting 9 as a spring constant. The square root of k over m now is 3. So omega is very near to 3. Is 3. Look at the attenuation here, that's related to gamma. And here the forcing is at 2. Maybe we can force it at 1. So look, the forcing now is low compared to that one. And sooner or later, this is able to go in phase. So amplitude and frequency now it's similar to the one that is forcing. They are going together, like myself, moving slowly. Let's try to go to very high frequency. Oh, cannot follow. Okay, like myself. Let's go to the resonance. Oh, now amplitude is getting larger and larger because the system is able to absorb frequency, to absorb energy, sorry. In the resonance curve, we are just at the maximum. And that's the phase diagram. It's 90. It's always, you cannot say out of phase or not out of phase. Let me go back to this. What is it? You see, when it's moving, there is no phase difference. Look here, 0. When it's very high, phase difference is pi. And it's always out of phase because it cannot follow. At resonance situation is 90 degrees, so pi over 2. And what is funny is if you remember, and if I delete attenuation, what are you waiting for? Disaster. Because without damping, this curve here has no limit. Because we have a singularity at the denominator. Wow. And if you go to the time domain, it's going to explode. Let's relax because it's a paradox. Every natural system has some attenuation. Okay, you see, simulation. Okay. Bang. Okay, to summarize this behavior, you can demonstrate that solving that equation and looking at that in the frequency domain, that's the transfer function. And that's the phase difference. We know that. Actually, if you imagine to remove damping here, this is going out, and you see that when omega is equal to omega 0, here we got 0. Bang. But it's not. By the way, what we can understand from this is that every inertial sensor will have a resonance. Good, but bad. Because we will be able to record better just the vibrations that are near to the resonance. This one, this one, this one, yes. And in principle, we're looking for a sensor that is able to record all the frequencies with the same quality. But with these systems, of course, we cannot because they have peaks, resonance. And there is an additional problem that if we want with these two expressions to go to long period, to 100 seconds, we have a problem. Here, we should have large k, it's over, large m and small k. It's a weak system, can break, can deform. Here, to get low values, what should we do? Can we change g? Actually, the answer is yes, but it's the next slide. We should get very long L's. Okay, go to Borgo Grotta and you have 100 meters made. Good, but you cannot. It's not easy to handle it. So the classical first arrangements of this part have to follow this. These are the two plots of the transfer function. You see this peak here, that's a resonance, the phase. And remember that if you follow the very high frequency compared to what? To the natural frequency, you got this solution here. Now the displacement is not that big, and you are out of phase of pi. And actually, okay, let me try to go back. What happens here if you pump high frequencies? That the two terms that will lead the equation will be the ones with the double derivative. Because remember, every time that you have high frequencies, derivatives will take over. So this and this. And actually, the displacement that you can measure there will be proportional to the acceleration of the ground, and actually you're feeling displacement. The two derivatives are acting. On the other side, if I move it very slowly, the relative displacement is going to 0. And that's why here, okay, the other term is taking the lead, so not the double differentiation in time, but the displacement part. And here, the amplitude is going to 0. There is no relative motion with the frame. So you are getting a very small signal, and that will be proportional to the frequency. So, okay, using inertial systems is fine, but they have two problems. They have a peak response, and it's hard to use them for long periods that are okay for seismology. The first solution was to, let me go very quick here. Okay, let's change G. How? With frames. Because actually, if you consider this system here, and you don't consider a pendulum, a vertical pendulum, but you put it in a frame, and you are, how to say, creating an angle here, this is very exaggerated. Actually now, the restoring force, I should have been writing it somewhere. No. Okay, here it is. But it's proportional now to the sine of the angle. Now with small angles, this is becoming smaller. Okay? And so the restoring force here is diminished. So you're going to long periods. In jargon, these are called as static systems. And this is the base of most of the instruments that have been used at the early times of seismology. Okay, now it will be a very quick journey through some historical instruments. I think this is the first official recording of an earthquake, recorded in Potsdam, coming from a signal from Japan. So after a long travel, well, okay, the system was going out of scale. I cannot pronounce it German, that's the original name, and it's really a mechanical jewel. And you see the frames here. Okay, first recording. Now it's 1889, but maybe the most famous recording is coming from this. Now we have to go on the other side. Let's go in Japan. And Bosch and Mori had been working together to build the system here. It was a sort of alliance between Germany and Japan. You see how beautiful it is. And now let's be recording in Tokyo coming from US. This is the 1906 earthquake, San Francisco earthquake. But if you remember, allowed Walter H. Wright to formulate the elastic rebound theory. But now we're looking at on the other side, the Pacific, and here again the answer of the instrument was going out because you see it was a pen drawing on paper. So the recording system had a non-linear behavior because it's no more a line. Okay, so it was out of scale. What's next? Go to OGS and you can give a look at a real Vickert one. It's a reverse pendulum with a big mass here, so for long periods. I think I added a link. There is a beautiful website. again. I found it. Wow. Wow, okay. Static. I think the first Google suggestion could be, no. Yeah, this one. There is a museum, as far as I remember. And here you go. Mutinga, okay. And here you see the first one. Now this one is working. Let's see. There is another. What is this? Wow. Okay, sorry, we can't lose too much time, but you're very welcome if you Google vCart and, okay, you will get that one. If you want to look at a real one, you can go to OGS. What's next? Okay, that's why we're making this crazy journey. In US, in California, there was a network managed first by Benno Gutenberg and then by Charles Richter that was using Wood Anderson. We had been working there. That's a beautiful instrument here. And that's why we are here, because this is the instrument that Charles Richter used to define seismology in 1935. Okay, that's it. Now, since it is an inertial instrument, it will have a peak response, a peak in its response function. It was about 0.8 seconds. Okay? And they knew this. So they realized that the definition of an amplitude recorded on this instrument is according to the instrument. So it's subject to its Fourier transform, its transfer function. Okay? That's important. That's why nowadays we call the original Richter's magnitude as local for two reasons. The first is that the tables, the numerical tables that Charles Richter prepared to properly define magnitude are California dependent, because these instruments were settled in California, and second, because they were connected to a specific instrument. This is the first message to take home. What's next? Okay, here we have a sort of the Soviet version, not yet Soviet, Russian, because 1906. And this is important because there is, maybe it's not so visible, because the principle is still that of an inertial pendulum. You see a big spring, good. Robert Hooke is working there, not only gravity. Big masses, but the masses actually, they were oscillating in a magnet. So ferromagnetic mass in a magnet. Okay, now if we move ferromagnetic mass inside the magnet, we create a current. I hope you do remember better than myself, Maxwell laws, and I think it's Faraday-Neumann, the one that is telling to you how much current you get from velocity. So you should say, so what? Well, that's important, because now with the wire, you can take that signal out of the room of the instrument. So you don't need a drum of paper or some photographic paper with rays of light that was the mess at the beginning. So you can take the signal out. And actually, after the 60s, with electronic circuitry, you can do whatever with that signal. And now you can use Wi-Fi. So a current is the key factor of the, let's say, post-Second World War instruments. That's why it's here. What's next? That's the scheme that you can imagine for an inertial one, but with this additional component. And that's a basic idea, because you can move now, you can displace the sensor from the recording system. At the beginning, you can use tapes, large tapes. Later, smaller tapes, digital tapes. Nowadays, flashcards. So that's the key. That's a key part. You can amplify the signal. You can do fast Fourier transform on this signal here. That's the key. Okay, summary of the first part of this lecture. This is a set of the response curves. Why response curve? So, yeah, let me arrive at the end of here. Why they are picked? Because they are based on inertial instruments. So they have peaks. Let's give a look to some Bosch-Mori, as you can see. Vickert, you see the peaks here. Look at the periods. And here there is an acronym that is important because it's connected to the next slide. This WWSSN is the first, is pointing to the first word network that we're going to look in the next slide. Yeah?
What's the role of the fast Fourier transform?
Oh, not yet, not yet. We are in 19...
But you said that...
Later.
The wave.
Because you can... I've been showing to you the spectrogram. Do you remember? Did I? Yes, I guess so.
Yes. The accelerometer.
I was playing with this silly gadget here in two ways. First, I showed to you the Green's function in different directions. Do you remember?
Yeah.
That was in time domain. But in no time, I can switch to the Fourier domain. Okay? Then I think I've been showing to you also the spectrogram. Definitely in the wave
My
physics.
concern is what?
What is FFT?
Yeah, FFT.
It's fast.
Fast Fourier transform, yeah.
FT is Fourier
So what's the
transform.
difference between fast Fourier and Fourier?
It's like the difference between me and Usain Bolt if I run. Do you know Bolt? Okay. He's fast. I'm not. In the sense that Fourier transform is defined, you can work it out for some signals using a pencil and paper. With the algorithms, the first algorithms implementing the Fourier transform, they were normal algorithms. Then Mr. Cooley and Takei in 1960-something, they created a fast algorithm to compute it. Don't ask me more things. And it is called FFT, fast Fourier transform. It's an algorithm. But in principle, it's giving to you the Fourier transform. Now, you two should remember when we have been recording here with the spectrogram. Do you remember?
Yes. You know the table, there were signals.
Okay. This silly gadget here, every gadget here, now it has a CPU that is computing Fourier transform in real time. Actually, every digital player is doing that. So FFT is essential to many signal analysis nowadays. But in the 60s, in the 50s, there was no FFT. Usain Bolt was not there. And also computers were just starting. So to take a signal and to analyze it, it was a revolution, but it was taking some time. Nowadays, it's like that. But up to now, no computers and no FFT. If you want FT, because Fourier was okay. So, summary at this point. We have a set of beautiful mechanical inertial instruments that are able to feel and record on paper or on photographic paper, or in some cases to something that is measuring a delta V, the motion of the ground. Okay? Problem, okay, they are beautiful, but you have peaks. And you have to use many instruments. For example, LP stands for long period. Why long period? Because the peak is after 100 seconds. There is an equivalent SP, short period. So you have to handle at least 6 instruments, short period and long period. What I was going to show to you is an old slide coming from WWSSN. Now it's called Worldwide Standardized Keyword. It was Standard Seismic Network. And you see the dots that were in the 1960s. It's not a word, because you have beautiful dots here, you have beautiful dots here, you have a beautiful dot in Trieste. Okay? You know why? Because here there was the Iron Curtain. So it's not worldwide, but you have to know that in this blank part there was and there is another network. So in the 60s, due to Cold War, essentially, we had a world collection of data, global collection of data. And this is the typical arrangement of a WWSSM station. You see, you have a Wood-Anderson, short period, a Benioff, short period, pursuing. So you have to handle a lot of instruments because you need a short period, a long period, and so on. Just for your information and to show you that also the wide Soviet Union region was covered with instruments. This is when I visited the Chisinau station, I don't know, is in Moldavia. You see here 60 instruments. And they're oriented in triplets, so north, south, east, west, vertical, a vector, with their response curves.
Sorry.
Yeah.
Can you go back one slide? The magnification on the vertical axis.
It's connected to the mechanical implementation of every of this. For example, definitely I'm not an expert, but for example, the Wood-Anderson was using a ray of light, okay, and a mirror, and then the photons, 1906, I think still a photoelectric effect was not studied and black body radiation was there. But okay, the photons, so it was not clear what was a photon, but the ray of light was hitting a photographic paper. Now, the leverage is decided by magnification. So each instrument had what in this formula here is G. That's the amplification. Of course, with the signal that is current, amplification is given by tuning, okay?
Okay.
But here G was on paper, so a leverage, or with light, but I don't know anything else.
So it describes the, let's say, amplitude of the
Yes. What is the problem, I guess, but you should ask to Wieland, is that G here is a constant, but in some cases it's becoming nonlinear. So like for example, when you have a pen on a drum, like in this case here, now G is supposed to work for tiny signals, but when the signal is large, So this is what I mean by G. It should be constant, but actually is a function of frequency. So if I got your question, you're asking about the amplitude here.
Yeah.
I think it's instrument dependent and by the mechanical settlement. That's a good question, but it's out of my knowledge here. So my answer here is about the G. To me is G. But G depends on how you settle your instrument. So Wiechert will have definitely a different G than Wood-Anderson. That is measuring photons on photographic paper. Okay? That's a good point, but I don't know the answer. The real answer. Now, there is a new, something is occurring in the 70s, the end of the 60s and the beginning of the 70s, computers. Big ones, but now are so funny, maybe you have to use the, I know the Italian word, but schede perforate, some forms. The beginning of the computers you had to code with strange piece of papers. I don't know the English word. Okay, good. So you have to write your instruction, insert, and I remember I've seen one with the memory that was a set of leverages. Every bit, not byte, bit should have been changed by hand, okay? Because you were changing the polarization of the magnet. By the way, in principle, a computer is using digits. Now, the revolution was the change from analogic signals, like what I'm drawing here, and digital ones. Good news. Do you say good news? That's a terrible analogic signal. How many data? Infinite. It's life, okay? Which is common. You don't need infinite. For example, here it's 0. It's not because you have noise. Why am I trembling? 0. Okay, how many values do you want to catch? Now the matter is about sampling time, right? And the key answer is
As much as possible.
in the 70s, the amount of data to be stored was crucial. Now we have a flash panel with tons of gigabytes, right? But at that time, how much? Yeah, I know. You're living in a digital world.
Kilobyte. That time.
My question is a little bit different. How much, which kind of information do you need there? The answer is, well, it depends on the frequency that I want to study. And the answer actually is related to what is called Nyquist or Nyquist, because he was a Swedish frequency. It's called the sampling theorem. Have you ever been watching to an old Western movie at the TV?
Yes.
Have you ever noticed that the wheels of the chariots are running in the... It seems that they are running in the other direction. Have you ever been watching at the old monitor of a computer with in a movie? It was... Why? If you stand in front of a cathodic tube, it's not, otherwise you get crazy, right? But if you... Why?
Because of the shots.
It's related to the sampling of with the recording, because it's taken some frames. Well, animation is based on how many frames we are able to distinguish. When we see a movie, actually we see a set of pictures in the classical art, but we see it as a movie, right? Why? It's important that we do not feel the sampling to watch a movie. So the real answer here is, okay, it depends. Let's take these samples, okay? Are they enough? Let's take one sample per second. What are we missing? Well, we are missing everything that is smaller than 1 second, right?
Yes.
Okay, Nyquist frequency is called this. I was assuming that you explored this in. Do you want a demonstration? So, if you take this sampling here, the largest frequency that you can record is this. Everything that has a larger frequency, you missed it, and it becomes an alias. And you see things that are not there. You're creating a strange reality. Because what is beyond this frequency here will be mapped into a lower frequency that does not exist. And that's why the wheels of the chariots are spinning in the other direction. That's why you see this strange thing. Because the a cathodic tube is using an electron beam with some scan, and when you take frames, you see it. But our eyes, how to say, they have a highest frequency, but not the snapshot of the video recording. Do you want the demonstration?
Yes.
Okay, let me try to have some improvisation here. Okay, when you sample a signal, it's like to multiply an f of t times a comb function. What is a comb function? It's a set of deltas, okay? If you multiply this by this comb of delta t, you multiply these two, you will have the signal in a digital fashion, right? Is that okay? If it is not, I will skip. If you want to digitalize this one, you multiply by a set of deltas, right?
Yes. Yes.
Okay. What is the Fourier transform of this? Convolution theorem. What is a product in one domain becomes the other product in the other one. So actually, the Fourier transform of this will be the convolution of f of omega, that is what we want, okay? Ft, this is f of omega, okay? Let's imagine that f of omega is this. Or a delta. Good, let's make it simple. Let's imagine that f of t is a beautiful sinusoid with a given period, okay? So the Fourier transform is omega c. Good? But wait a second, if we apply a digital filter here, what we got is not this, because we will get the samples. What is the Fourier transform of a comb? That's easy. It's a comb with spacing 1 over delta. What does that mean? That now, instead of having one peak here, we have many. Infinite. And they are reproduced every 1 over delta t. Now, is that fine? Yes. Until the second one is out of the game. Now let's take a small delta, t. These are getting nearer and nearer. And maybe they overlap. Maybe this one is coming here. That's an alias. Because now the repeated spectra are coming inside what we want to see. And we see them, but they are not there. For example, let's take a sinusoid. It's fine until you sample like that. Okay? You are still able to see this one. Good? Actually, you have 2 samples per cycle, but if you sample it at lower, maybe you can sample this, and you will have something like that. Oh, the delta is entering here. So they have to be spaced at least of 1, 2 over delta t. That's Nyquist. So the answer to my question is, how many samples do you want? You said 1 gigabyte, whatever. Everything depends on the maximum frequency that you want to study. Do you want to study 10 Hertz? Well, you have to take at least 20 samples per second. That's why GPS couldn't be used in the 80s to study the ground motion, because the sampling was 1 at second. So what is inside was missed. But nowadays, GPS are sampling 20, 100 times per second. Good. And we can use them as seismometers. So actually, my question there is, nice. We have a digital world, we can store data, we can manipulate data, big data. Okay. But let's remember that in the early times, sampling was crucial. So you have to sample at least twice the period that you want to study. Long periods are fine, but short periods, now it's a problem. Because you have to take at least, let's say, 20 samples per second. Big data. That's why the early accelerometers were based on triggers. So they start to record only when the signal was there. Otherwise, you have plenty of data. You don't know where to store them. Early times. Now I don't know. There is an additional problem. So you see how convolution theorem can be very quickly used to understand aliasing. There are two other things to be remembered for digital signals. There is another feature here that has a practical impact on instruments that nowadays is overcome. Because if you want to sample it, that's fine, but you have also to store it. How many digits? Let's imagine to take 1 byte, 1 bit. It is 0 or 1. So all this beautiful signal here could become 0, 0, 0, 0, because it's here, and 1. That's your signal. Okay, give me some money and let's use 2 bits. Now you can go to 4, 8, 3 bits, 4 bits. So remember, there is also a sampling in amplitude. And nowadays we have 24 bits to store things as a standard. Question to you. What is the dynamic range of an instrument with 24 bits? Dynamic range is measured as the logarithm of a maximum amplitude over the minimum amplitude, like the decibels. Actually, it's measured in decibels. And that's why, let me show to you. So Nyquist frequency, we did it. Okay, it's 1 over 2 delta t. The second part is good old friend, decibel, but actually we've been using to measure the intensity of sound. Okay, now we use it in this fashion here. 20, the logarithm of the maximum amplitude over the reference 1. And you see, according to the number of bits, decibel, that is now expressed in dynamic range, is telling to you what is the resolving power in amplitude. Now it's very large. But at the beginning, maybe it was not that much. Okay? 20 is coming because it's amplitude and not energy. Please do remember that energy is always proportional to the square of amplitude. Additional comment that maybe will be useful, well, not very much, maybe, just to show to you also the other side of the story and another possible use of convolution theorem. Let's take again our beautiful sinusoid. What is it starting? What is it ending? Minus infinite plus infinite. We have no time. So usually, we record our signal in a time window. But we cannot measure from minus infinite to plus infinite, right? Okay, what is the price to pay? Now you can answer. Because now, to take that signal there, is like to take the initial one, f of t, times a boxcar, right, of a duration t. Now you know what is the Fourier transform of a boxcar, don't you? And it is
Sin expense.
A boxcar. Okay, is it this?
we did it during the last lecture.
Sin expense.
The sync function. I think you're saying, okay. I was checking on Google, and actually, if you
Yes,
if
the
you Google,
sync function.
Sin.
well, let me do on the other.
Boxcar.
Not this one. There should be also
The mathematics.
Postgraduate function. I think I found it. Okay.
Boxcar.
And one of, you see, it's nice. You can define it there. And then there was a place where I was going to cut that one. It's in Italian, it's not pronounced. Oh, it's called rectangular function, but it is. Yeah, it's the same, of course. So if you define it in this fashion here, it has a duration, unitary amplitude. Fourier transform, here it is, it's beautiful. We found it for two boxcars, rise time and rupture time. We discovered that the first lobe is the most important one, and its first zero is related to 1 over the duration, 1 over 2 duration. Okay, so what do we have here? Instead of having a delta, now we have to convolve this with the Fourier transform of the boxcar. What is the price to pay? That instead of having a beautiful delta, a beautiful harmonic in the Fourier domain, now we have a group. We have something here. What about its width? It depends on t. Longer t is, sharper this will be. If you let t go to infinite, this will become a delta. If t is very short, oh, this is spreading. Problem, if you have 2, and we are too narrow, you are missing this. So another message to take home in general is that thanks to the convolution theorem, multiplication becomes a convolution, we can understand that the resolving power in the transform domain is related to this interval. The resolving power in the time domain, that is the sampling, is giving to you the maximum frequency that you can look here, Nyquist. So you see how the two domains are always entangled. So delta t decides maximum frequency, maximum t decides the resolving power. That's the end of out of the slides. Okay. Just to tell you what, that these simple concepts here actually have been reached until the 1980s. For example, an IRIS project was developed in high school in USA, and that's the building. Now we understand everything. A frame, a spring or something that is creating a restoring force, a coil inside the magnet, with a current, with a response function. That's the new part. Now the signal, that is a delta V, can be digitized. And we can apply Fourier transform, and after 1968, fast Fourier transform. And just an algorithm to efficiently perform the Fourier transform. Okay, so we're done. But up to now, we have been looking at what we can call a passive seismometer, like this one. And I will cut the long story short, telling that after the 1974 something, and after the 80s, the new broadband seismometers have been created. Because now here, I'm moving, let's imagine that I'm moving with the background. Okay, it looks silly here. And this is passive, because now the response that I will get from the difference between this and me moving is related to the length of the bar, to the K of the spring, to whatever, right? Can we make an active seismometer? Yes, and the answer in principle was very simple. It is taking advantage of a strong development of electronic circuits in the 70s, but the idea is very nice. Let me show it to you. They are called force balance or retraction principle instruments. Now, this is the scheme given by Wieland. It's very simple here. But the key part is not new, is this arrow here. Now, you have a black box, linear system, beautiful, we know it. But we have never imagined a feedback. Also because you are breaking linearity in principle. So it's a system whose reaction depends on its output. You have a feedback. It's like a thermostat, okay? The value is changing with temperature, I hope. Something like that. And that in principle is breaking linearity. It's like when you listen to that very bad whistle that is called Lambert whistle in the microphones and speakers. It's exploding, it's terrible. And you have to move out the microphone from the sound. Because the box is emitting sound, you are emitting sound, it's entering into the microphone, it's entering and it's exploding. It's a feedback. Larsen, it was Larsen effect. Okay, by the way, let's imagine now, and that's the key idea of force balance seismometers, that instead of measuring the mass that is moving, can you imagine a Vickert mass? Oh, no, it's turning, but it's hard to handle it. Let's simply measure the force necessary for that mass to stand. Can we do that? So at each time that I'm moving this one, someone is computing how much force is needed to keep this standing. If you are quick enough, at every time you can balance the force that is forcing the mass with an advantage. If you measure that force, you know the acceleration. And you have no more masses moving. Okay? So it's a feedback. Instead of measuring the motion of a mass, you measure the force at each time necessary for a mass to stand.
Is it positive feedback?
It's not positive, it's tuned feedback. Let me show to you.
Because it will the page.
A very simple example. Look, let's take a box. Could be our pendulum, could be our inertial system. And now let's take the output back to the input. And let's, for example, sum it. Now y will be a function of x and also the answer of phi1 that is passing through phi2. If you put these things together, now the transfer function of this feedback system will be not only phi1, but it will be phi1 times phi2, it's here, because that part is linear, and summed. You can demonstrate that this is the answer, because that is the net response. You should say, so what? Okay, let's take our seismometer, and let's take this system here, just a multiplicative factor, let's plug it back. Now the Fourier transform of a transfer function is this, the one we have been using, this times k, and so that. If k is 0, we go back to our system. Okay? I'm moving, sorry. You have to measure that one. This is just a principle. But if you tune k now, changing it at every time, you can create a system that has many different responses, right? If you change k. No k, amplification factor, okay? The old response function. But if k is smart enough to change it in real time, in principle with the tuning, you can change the answer of the system, right? You can imagine to have okay, inertia, changing k, you can move it, and you're creating a flat line. That was the idea of a force balance, created by Wieland, and thanks to the electronic circuits, now the mass are no more moving, but in each time you're measuring the amount of force necessary for that mass to stand at all the frequencies. It's like changing very rapidly k. As far as I remember that I'm a poor theoretician, so don't ask me the real implementation of this. So that's the change. So now your omega 0 is k dependent. The scheme is this. It's called leaf spring. Now you have, it's like if you have a mass like that one, with a spring that is connected in a very delicate way with that one. But now k disappeared, can be very low because it's not, the mass is not moving. But in each time, you're measuring the k necessary for that mass to stand. So you don't have to control the mass that is moving. That's the key idea. Thanks to circuits. Let me show to you, that's why it's called an active sensor. MEMS. Let's be understood, guys. No advertisement here, but okay, I think it's this one. Okay. Now if you open, that's an old version, no advertisement here for any, just an article that I was reading there. Okay. That's the mass and that's the spring. Now it's so tiny, but so tiny that it's embedded in a small circuit. That's a mass with a spring, okay? But the circuits can make the K with feedback changing very rapidly, so it's not necessary for that mass to stand. So in principle, you can use any mass with any K. That's just the principle. The message to take home is that with force balance seismometers, for example, Giovanni se ne aprite, sorry for the Italian, but she's using some of them. Se voi aprite uno di quelli, vedrai una molla a foglia con una massa un po' più grande. Just to tell you that what is really changing is that now the line is, okay, flat. That's the name of two brands that are producing broadband seismometers. One is Strakais and the other is Gural. No advertisement here, I don't buy instruments. But just to tell you, look at the difference. The line of the response of the instrument in principle is flat. So you can measure all the frequencies with the same instrument. That's the future of the present of force balance seismometers. Okay?
Up to that flat band here.
Of course, in reality, they have corners. For example, for very high frequencies, it's better to use accelerometers, because you know that acceleration is, okay, high school physics. Let's take every time that you make a time derivative, you're taking out I omega velocity minus omega square acceleration. So the signaling acceleration is much richer of high frequencies than displacement. That's natural. High frequencies means that maybe if you want to record 100 Hertz, you can use accelerometers. Now let me go very fast with some, because otherwise we have no time to continue on the next. So it was just a very quick journey through seismic instrumentation. We need the classical ones to understand magnitude defined by Richter. These cartoons here just to understand how a seismic signal in principle is made. For example, this is coming from your textbook, a very important feature that is common, usually body waves are rich of high frequencies because they're impulsive and they contain many frequencies. Surface waves, like Rayleigh waves, love waves, they are, some modes of them, especially the fundamental mode, they are coming later, I hope you do remember, they are dispersed, and if you give a look to these different portions of a seismogram, the spectrum is different. For example, body waves, they are relatively higher frequency than surface waves. This is important because MS, that will be defined as the magnitude connected to surface waves, will be defined at 20 seconds. And B, that is the body wave magnitude using body waves, will be defined at 1 second. That is a shorter period than 20.
So in theory, you should analyze the whole seismogram in terms of spectrum?
In principle, you have to take all of this. But if you go to the frequency domain, it will be very messy. That's why there are different ways to analyze seismograms. Or, well, noise is different, but okay, seismograms. It's better to divide, for example, the early arrivals. So you can use a time window filtering and look at the spectrum of body waves or of single arrivals, because you can easily separate them in time domain. Later, what is coming later and dispersed, you can separate with time window and then to analyze it in frequency. But there is an additional feature that to analyze surface waves, the best way is to do what is called frequency time analysis. I don't know if you know it, but it's called time, but it's a combination of them because you want to study dispersion. So you go back and forth between time and frequency domain. To sum up, you can use time windowing, Fourier transform, and then to study these separately. You can take the whole, but it will be messy because all the time information has gone into the phase spectrum. And if you have ever been looking at the phase spectrum of a signal, it's a mess. It's pi minus pi. So it's better to operate first in time, then in frequency, maybe going back and going back again. That's called frequency time analysis. But message to take home is body waves and surface waves, usually they have short periods and long periods. 1 second, 20 seconds. Let's remember for the next lecture. What's next? The same signal will appear very different on different instruments. Why? Because the classical ones, the inertial ones, they have response curves that are very peaked. For example, look at this. It's the same signal. The P wave part, it's a Romanian earthquake recorded in Germany, but look how different it appears on a short period, old-fashioned instrument, long period, and a broadband. In principle, a broadband is containing everything. It's flat. What you can do with the broadband, you can simulate the old instruments, because what you have to do is to go to the frequency domain and multiply by the response curve of the old instruments, and you will get this too. The same is here. Long period, short, long period again. Look at the different magnification here, and this is a broadband. So remember that when you look at a seismic signal after being recorded by an instrument, you have always to deconvolve the instrument before looking at it. It's called instrument correction, especially for the old ones. What's next? Oh, that's nice. For example, look at the first. It's the recording now, we're in US. Vertical ground motion, remember, in any case, a seismometer that is recording displacement is measuring 3 components: north, south, east, west, vertical. And the same velocity acceleration. Look at the broadband as it can be filtered into the long period part and the short period part. Wait a second, this is the amplitude this time 10 times larger. But it's the same signal. But just looking at it in different frequency windows. Look how wiggly is this. Okay? And I love this one, also if it is a terrible signal, because this earthquake has been, unfortunately, very well studied, because it's the Michoacan September 1985 event. Magnitude, still we do not know what exactly is MW, but let's say it was a large earthquake. And these are the recordings just near to the source. The distance to the fault was, let's say, around 10, 20 kilometers. Let's give a look to them, because this is an example of what we can call strong motion seismology. I added in the last 2 days a couple of slides to the slides that you have here. Just a couple of slides about the definition of strong motion seismology, because it will be important. By the way, so the definition is coming next. Let's give a look first to these 3 triplets. Why triplets? Well, 3 components of the motion: vertical, east, south. Okay? But let's give a look to them in the acceleration domain. So please remember units here. Engineers prefer to use G because they can convert immediately with 1G. So building should sustain 1G, its own weight. The most common unit here is centimeters per second square, so this is roughly 0.1 G. Look how wiggly the signal is, very rich of high frequencies, very rich. Let's go to velocity, centimeters per second. Now the signal is a little bit simpler than this. You see these large lobes here, this is directivity, and now you know in principle what it is. Because near the source, you can feel that. Let's go to displacement, centimeters. Oh gosh, what do we have here? Now you know what is that. That's near field. You see it? Okay, so you have, let's say, 70 centimeters. The pen of our system is not going back to the equilibrium, so you can measure this, but actually it will be moved of 70 centimeters. So near source, here, these lobes here, and near field. Now, why this signal is so important? Because usually we do not look at this for this event here. And I hope to be able to show to you this recording in Mexico City. Mexico City is located 300 kilometers from Michoacan, more than 300 kilometers. So you should say, 300 kilometers is a huge distance. We have geometrical spreading, we have Q, wait for the next week. So that signal should become so small. Who cares? Actually, it was amplified by what we call nowadays side conditions. And that signal has been amplified at given periods, and resonance had been killing more than, I think, never been accurately estimated, but 30,000 people in Mexico City after 300 kilometers. So usually, pardon? It was a... Okay. Yes, it was impressive. No one, well, almost no one was thinking that a signal at 300 kilometers could be hazardous or risky. Let me open it. I think I added the slide in seismic hazard. And usually I use this signal as first. Oh, there you go. Look. That's one of the signals that you have been looking at. You see? If you want to take the peak of that signal, it's called PGA. Okay? 0.15 G of PGA. Why PGA? Well, it's the most adopted parameter for hazard. Most times, peak ground acceleration. So you take the peak. Okay? Now let's give a look to the signal. Okay, it's going. Oh, it's nothing here. You will discover that an elasticity will affect essentially high frequencies. So longer the wave is traveling, more high frequencies will be absorbed. Oh, nothing is here. Uh-oh. Look at this signal here. Now it has pretty much the same amplitude, but with a totally different periodicity here. Because the local side conditions had been taking the low signal that was left with tiny amplitude, but it was still containing something that was about 0.5 Hertz, around 2 seconds as a period, and amplifying it. And the signal was amplified by sedimentary basins, because Mexico City was called Tenochtitlan, and it was built on an ancient lake with a 200 meters cover. It was a lake. It has been reconquered, and reconquered. So amplification and resonance with tall buildings of around, let's say, approximately 20 floors. They were new buildings. So this is leading to seismic hazard. So usually, Michoacan event is studied for this. But what I've been showing to you is the near source, near field effect. That part is nowadays called strong motion seismology. Now you should ask, what is strong? Please ask.
What is strong?
We don't know. But I was taking these statements from a beautiful John Anderson paper. Strong is something that can be hazardous. But the traditional definition was connected with the old instruments, old accelerometers. So strong could be something that is making humans to feel it, okay? So we feel shaking, and can affect anthropic systems. How much is strong physically? That's not easy, but at the beginning of strong motion seismology, everything was related to 1G. Now, what is the upper limit for accelerometers? Okay, it's, let's say, 1G. What is the lower limit? Well, that was connected to the instruments able to record something that was felt by humans. And it was around 0.01G. But also for instrumental reasons was the tiniest amplitude that could be recorded on accelerometer in the 70s. Because actually it was the lowest one going beyond noise that you can measure or on photographic paper or on a drum of paper, and the lower one was approximately 0.01G. So classically, strong motion seismology is taking care about motions between 0.01 and 1G. But nowadays, there is no limit between seismology and strong motion seismology. So strong could be everything that is, every signal that can be hazardous. Okay? So it depends also on indirect resonances. I don't think that you have the slides. That's my guess because I added them 2 days ago. Just to conclude this part, I will grab from you some minutes because I want to finish this lecture to restart on Friday for an important one. I will be very fast. We will not enter into details. One thing that you have always to remember, every signal, every instrument has noise. You should say, okay, it's fine. It's like something when you have a speaker. What is noise in seismology? That's funny, because classically you can have noise coming from every vibration that is not an earthquake. Like, for example, the sea that is, how to say, crashing waves on the coasts. It had been first found in Uppsala, because there was an observational point there with many waves. So you have natural noise. You can call it noise everything that is coming from tiny earthquakes, like microseisms. Or you can call it noise the traffic. Everything that is related to human activities, or wind that is making the leaves of trees blowing, whatever. Whatever is not a signal. And this is the typical spectrum of noise, distinguished by short periods, intermediate periods, long periods, that is not a signal. What is funny is that in the last 20 years, what was noise now is signal. And with people that is working with seismic interferometry is using noise recordings to extract the Green's function of the medium. Maybe Stefan will speak about that. So you have to remove the earthquakes. So the distinction between noise and signal depends on what you're going to analyze. Classically, it is whatever is not an earthquake that you want to record. So it could be a microseism, could be anthropic noise, could be waves on the coast, but nowadays it could be an earthquake. But of course, this is giving to you a limit beyond which you are not able to feel a signal. And this is also at the base of the magnitude definition of Charles Richter. To conclude this lecture, the old plot of the dots of the WWSSN, the world was divided in two. Nowadays, it's complete. So this picture, I think, has been taken, if you want, the update is this one. We have a really global digital, so global, really, digital network. And the standard settlement, okay, that's the update in 2019. Oh, it was not so well overlapped. 15, 10, okay. On this, let's see if it is working. You should be able to find the evolution. Maybe it's not working. Yes, okay. And this is going until, okay, I think it's updated, okay? But the message here to take home is that nowadays we have a global, really global, and digital network, okay? And this is the typical arrangement of beautiful modern instruments. For example, now we have broadband. Now you see how they are made, tiny. Some narrowband, it means that they are focusing on some specific frequencies. Primary, very broadband, flat response functions. Okay, they are able to measure a lot of things here. Strong motion, usually they are accelerometers. Ancillary, okay, you may have a GPS, maybe it could be reverse, so you have a GPS station and a seismometer there. And what is important, okay, power and communication. Nowadays, most of the signals are traveling without wires, and it's digital. Just to tell you how things have been changed since the WWSSN. And there are important arrays. The first one was the US array. That was one of the. We have been using the animation from the US array to understand some features of wave propagation, if you remember. Okay, you can. Let's see if it is still working, this one. So US array means that you have, okay. We have been using it also to understand the interference between progressive waves to generate free modes. That's an array. So it's not only one sensor, but it's a network of sensors. You may have different scales. You may have a small scale. For example, this is in the Gran Sasso laboratory in central Italy, where we have a very important laboratory for neutrinos studies. And there is a seismic network because this laboratory is very near to the Apenninic faults, and so it's an array because it's communicating. The instruments are communicating, so it's the new development. And the last slides are just giving to you some general messages. And this is a new version of this. So GSN, Global Seismic Network, digital. And the message to take home here is the following. Look here, that's the period scale, the frequency scale. Now you see for seismology, it's important to go from the longest ones, the free modes of the Earth, till the shortest ones. Okay, what is that? Could be also the 10, 20 hertz for engineers. That's why it's here, 0.1. At that time, this was the WWSSN that was able to cover this range of periods and this range of amplitudes. Look again the definition of amplitude relative to a basic one using decibels. So remember, still, if you remember, we used the original decibel definition like that. I hope you do remember. It was introduced to explain our different sensitivity to intensities for the human hearing, and I0 was a reference intensity, 10 to the minus 12 watts per square meters. Why that number? Because lower than that, usually we're not able to feel that. And before reaching the pain of the threshold of pain, that was 1 watt over square meters. So we said, wow, we have to take with us 12 zeros. No. So we use a reference intensity. The largest one is giving us 12 powers by 10, and we have 120 dB. 0, 120. Please do remember that there are sounds with negative intensity, because It's sufficient to have an I less than I0. We will not hear them, but they are there. Negative decibel, like the magnitude. Okay, intensity is the amount of energy per unitary area in unit of time. Energy is related to the square of the amplitude. So you can always define this like that. Okay? 240. That's why usually you get this. So we have been using today the same definition of decibels, but to express the maximum amplitude related to a reference one. So this is nothing else than a scale of powers of the sensitivity of our signals. It's huge. And what I wanted to show to you is the difference between the modern time and the old time. And let's remember also that we have here motions that are beyond what we do feel with strong motion or with long period, because for example we have other secular motions like earth tides with 12-hour periods, or we may have tectonic motions that are longer. And that's the, how to say, the blurred border between modern geodesy and modern seismology, as you are discovering, I think, with Alessandra. Okay? So you can use GPS to study the strong ground motion, but also long period deformation, post-seismic, pre-seismic, so longer periods. Here we have one parameter that we are not able to describe, because there is magnitude. And magnitude appears also here. This is an old-fashioned plot that is nice because it's showing to you not period but frequency. Okay, so it's reversed. You see how frequency can go up to 10 Hertz, maybe 20, maybe 100, that's acoustics. You can go here. That's the, again, acceleration in terms of g per second square. So you have a different unit, that's why I was overposing these two, but they are expressing the same feeling here. Noise, you see this peak is due to the microseisms and the motion of the oceans on the coasts. These are giving this peak here. So we cannot feel something whose amplitude is less than this. That's noise, natural noise, that is reported here. And what we have left here with something that is related to a parameter that we will need to introduce the next lecture, magnitude. How much energy, because the amplitude of the motion will depend on the energy released by an earthquake. Next lecture. Final slide is this one. It's an old one, but I leave it because it's funny. Complete ground motion, phenomenon of interest. Let's give a look to this, okay? Frequency. So wave propagation, dynamic rupture, that's our domain. Remember that you may have very low frequency signals like slow rupture, after sleep, or post-seismic deformation. You will study it with Karim. And gravity, strain, tectonics. Why I've left this here? Because at that time, GPS was not able to record displacement with a sufficiently short delta t. That's why here we have a dashed line, because the sampling was maybe 1 second, so you couldn't use it to measure an earthquake. But beyond that terrible cartoons that had been plotting, you discovered today that if you have a sufficiently short delta t, you can extend your maximum frequency, your maximum accuracy frequency. And nowadays, GPS have a sampling time that is well sufficient to study ground motion. So you can take this line, this dashed line, and fill it. Okay? So I've been leaving this slide here just to remember you that seismology is one part of the story. The border is blurred with geodesy, is blurred on the other side at very high frequency, here with engineering for buildings, for example, and that's it. Okay, what we have been discussing in a messy way today, in a very fast way, is a sort of the accumulation of tools for the next definition, that is magnitude and earthquake energy. So it's Friday's topic. Okay, sorry for the 10
One
minutes.
small question.
Yes.
The previous slide, and what is low gain seismometer?
I'm going to crap now.
What is it?
Low gain, the top part, yeah, not lower.
I don't know in practice. In principle means, okay, high frequency broadband, it means that you're going at high frequency. Low gain, I don't know, I think it's 24 bits, I know, because now you know that 24 is the new standard for the resolving power in amplitude. Low gain, I think it's so sensitive that you don't need a large G, but it's my guess.
It's sensitive or not? It is sensitive.
I think it is so sensitive that the G has not to be very large. Lowest and highest for VBB, so VBB is this one, wait a second. Okay, STS1, so it's this. I have to admit that I was copying the caption from the proper picture.
Yeah, I mean, there's the yellow part which is like covering quite much period.
Low gain in this sense, but if it is high gain, you cannot record this because it's getting out of scale.
So
That's my guess.
So what is gain here?
What in 10 again, this G. So low gain means that you do not need a large G there, and remember that G is entering here. Okay, you need a larger G when you want to amplify the signal, right?
Yeah.
Okay, so you're taking the amount of departing of a ray of light on a photographic paper is, of course, depends on the distance, right?
Mm-hmm.
Okay, so a tiny motion here, there is getting like that.
Mm-hmm.
That's large G.
Mm-hmm.
Good? So it's this G and it is this G. A low G means, okay, if I take nothing, you will record that, right? Low gain means that you're not using here a large G because otherwise a large ground motion would be out of scale. This is my guess. Are you getting my point?
Yeah. I mean, I guess.
Let me give to you an unpolite answer. Ask Stefano. I am sure that he knows. I'm sure.
Okay.
I'm sure. So, let's meet on Friday, and I think I can push this. But now it's blinking.